Alright, welcome back to Scholars Forum. Let us continue from where we stopped. So now we're going to be finishing the very first part of our work, set theory, elementary set theory. So we're going to be working on Venn diagrams now and on the operations of sets. As we have the Morgan's law, identity law, whatever law, and all the laws and the laws. Not as many physics do, but then all the laws are joined. Alright, so let's start with Venn diagrams. What are Venn diagrams? Alright, now let's see, what are Venn diagrams? Venn diagrams are diagrammatical representation of sets. Okay, now in this instance, say for instance I have A is 1, 2, 3, 5. Okay, and I have that B is 2, 4, 6, and 8. Now I have been told to represent this with a Venn diagram. Now a Venn diagram, how does it look like? What is it? Let me show you something. Now, Venn diagram is like this. Now, I'm sure some of you observe that I left a space in between here. Now, that space is where I'm going to be writing my universal set. I'll come again with this sign. Please, let's not use this, all right? Now, let's use this. Good. Yeah, well, now, let's assume that you didn't see the first part of the writing. So, this is the part you saw. Okay, now, in the universal set, it's going to be holding here. Now, we have the first set that belongs to A, and the other set that belongs to B. Now, I could draw my other set belonging to B like this. Okay? Now, before I can even actually know whether to join these two things together, I can check from the set that I was given. Okay? The set of sets that I was given. I hope you understand English. Now, this is 1, 2, 3, 4, 3, 5, and this is 2, 4, 6, 8. And you can observe that I have 2 and 2 common here. So that means I have an intersection. Now, if you're just joining for the very first time, that means you have to refer to our very first video under elementary set theory. Now, the intersection between them is what? 2. So that means 2 belongs to what? A and B. Now, what is specifically for A now? Looking at A, 1, 2, 3, 5. That means 1, 3, and 5. Of course, you can't see them in B. So that means they belong to A, 1, 3, 5. Now, if you look at B, you have 4, 6, and 8 that does not exist in A. So that means you have 4, 6, and 8. Who is smart enough to tell me why what I will call 1, 3, and 5 and what I will call 4, 5, and 6? Now, I know you've guessed the answer and some have guessed the answer correctly. Yes. So that the answer I got here, 2, 1, 3, and 5 is what? A different B. Am I correct? I believe somebody has noticed the similarity. And the answer 4, 6, 8 is B different A from our very first class. Alright, so you can see how each of the rows and the elements and all the works from set theory are interlinking in every part of it. Okay, so this is how you represent these two sets this way. Now, if you are given a set and you are told to show A union B, how do you show that? Now, let's have to show A union B. Now, do not forget that this is A and this is B. Now, the whole of A is this. The whole of B is this. Now, if you do understand what we have been doing so far, you will understand that this line that covers like this is still A, and this one that comes like this is still B. Therefore, if I'm doing A union B, I have to shade every single part of it, A plus the intersection plus the union, all together, plus the difference and everything. That is A union B, joining two sets together. Now, when you talk of A intersection B, A intersection, so let's see A intersection B. Now, A intersection B means what does A and B have in common? Now, if you observe, this space does not belong to this space, and this space does not belong to this space. So automatically, the only thing that they are sharing is this place. So this is A intersection B. What is it that A has that B also has? So that is what we call this part. Alright, I believe that we are good with this. Now going further, we have what we call A complement. Now for A complement, let me make use of the blue marker. I think the black is fitting already. Now for the A complement, just one. Now A complements, this is A. I've been told to do A complement. Now this is A, alright? So A complement is whatever is not in A. And whatever is not in A will be here. Whatever is not in A. So anything outside A is A complement. Same thing goes for B, B complement. Whatever is not in B stays outside. Now let's go for another one here that says A intersecting B complement. Now we've been told to prove A intersecting B complement using a Venn diagram. This is A, this is B. Now I want to break this thing down into two parts so that you will not get confused on how I'm relating this works. Now initially we should have A and initially we should have B. Now A intersecting B complement. Now B complement will be what? Anything outside of B. Correct? So anything outside of B is B complement. Now I have now been told, okay, anything outside of B is B complement. That means B complement first now. B complement will be this. Somebody might ask a question as to why I'm not shading the inside. The reason is because what we are shading on the inside also belongs to A. So at that point you cannot call it what? Also belongs to B rather. So at that point you cannot call it B complement. So B still extends here. Now remember this place here? B extended here. A extended here. That's why we join them together. Okay? This place B extended here. A extended here. Okay? So in this particular part now, B complement is anything not of B. Okay? Now, that's how we should do what? A intersecting B complement. Now, this is B complement already. Now, where is A? This is the whole of A. This is the whole of A. So, the whole of A intersecting B complement. B complement is already here. And this is still A. So, this A intersecting B complement will only remain this space. Now, somebody might want to ask, since it is A intersecting B complement, why did I shade this place? Now, I couldn't shade here because this one was not shaded together with the first function. Okay? So, this is A intersecting B complement. I will go there. Alright. Then, that's all we can take on that. Okay, I think we can take one more. A union B complement. Now, A union B. A union B all into complements. Okay? So now at first I have to first join A and B. If I join A and B, now let me use the black marker for that so that I could use the blue marker to show the complement. Now the black marker represents the union that you are seeing inside. Now if I am to join A and B, I will have this. A and B. A, B. Okay? Now follow me now. So that I think this was terrible. Alright, now follow me now. A union B is this already. Complement of it. What does complement mean? Whatever is not in the set. So that means the whole of these places that are not in the set is what they asked us to show them. So, as you can see, if I remove this away now, removing all of this away, you can now see the final answer. Alright? Okay, I think I'll have to withdraw. Oh, now my illustration is looking so small. Okay. I think I can manage this. I'm not an architect. Alright. So this is your A union B complement. And now with this we close the session for Venn diagrams. If you have questions, you can just drop your questions under in the comment section and we will get to you. Make sure you are liking and subscribing to us. Don't forget that. Now that will give us more of the morale to come in for more. Now, another law states that when the laws, or sorry, let's say the operations on sets. Now, there's what we call the idempotent law. That law states that if you add an element to itself, you always get the element. If you intersect an element with itself, you always get the element itself. That is true. If I add 1 to 1, now actually in sets, in this case. Okay. So if I add 1 and I still have 1, then that means I still have 1. If I have 1 against 1, then I still have 1. Okay? So let's use a practical example. Let's use this set. 1, 3, 5. 2, 4, 6. Now, A union A, 1, 3, 5 and 1, 3, 5. Don't forget, set said it doesn't want any repetition. So that means we'll end up having 1, 3, 5 again. Okay? Now for B, if I intersect B against B, 246 intersecting 246 is still going to give back 246. And that's what they call the idempotent law. Now the next law, the associative law, says that A union B union C is the same thing as A union B union C. Now you can observe the flow in how I was saying it, okay? A union B is in the bracket, union C outside. It is the same thing as A union B into union C in the bracket. Alright? The same thing goes for intersection 2. A intersection B intersection C, giving you A intersection B intersection C. Okay? This is the associative law. Then we have 3, the commutative law. And that says A union B intersection C is equal to A, sorry. Let's not confuse ourselves here. This will give you A union B equal to B intersecting A and A intersecting B equal to B intersecting A. Now, when you do your union and your intersection, you observe that when you add your A to your B, okay, it will be your B intersecting your A. And when you add the A to B, okay, intersecting B rather, it will be, this will be, so it will be A intersecting B will be union A. Okay, now let's go further. Distributive law. Now the distributive law, for the English alone, that looks kind of, distributive law. Now A union B intersecting C will give A union B intersecting A union C. The same thing goes for A intersection of B union C. It becomes A intersecting B union A intersecting C. Alright? So for the idempotent law, the associative law, the commutative law, or the commutative law has an issue here. A union B is the same thing as B union A, and A intersecting B is the same thing as B intersecting A. Sorry for that error. Alright, now it's balanced. Then the distributive law, yes, that's how it goes. So that means when I'm doing an A union A set combined together, what it means is that the sign in between them can affect both signs on the outside. So it will be A union B intersecting A. On the edge here, A intersection B union C. It will be A intersecting B, okay? Intersecting A union C, okay? All right. Now that's almost everything. We still have identity law. Now, identity law is actually straight to the point. What identity law does is that when you add A to an empty set, or when you add an empty set to A, it is still A, okay? So in identity law, let's find a place to write that. Alright, so we have 5 identity law. Okay, so when we have A union an empty set, A intersecting an empty set, what else again? A union universal and A intersecting universal. Alright, now for A union empty set, it's an empty set, so that means there's nothing to add. So it will still remain A. A intersecting an empty set, nothing to check whether they have any similarity or not. So it will still be A. But then, what happens when A is joined together with the union? Don't forget, union is the father of all the sets. So that means automatically the father will be our result. Okay? Now for A intersecting universal sets, what does that mean? It means what is in A that is also in the universal set. Now you will agree with me that the thing that is in A that will be in universal set is A itself. Okay, so let's look at this example. You have universal sets 1, 2, 3, 4, 5, and you have A to be 1 and 5. Now, looking at this, someone says I should now do A union universal set. Now, I already have 1 and 1 here, so that one's not a problem. I have 5, not a problem. At the end of the day, A union universal set will give me back universal set because 1 and 5 is already here already. So if I add 1 and 5 here, I'll be repeating numbers, which is not permitted in sets. So at the end of the day, you still have your A. So that's why you have that here. Okay, now let's go further. Our side, we have the involution law. The involution law. Now, what does this law state? It states that when you have a complement and you take the complement again, what happens? The complement terminates the complement, giving you back the elements. That's all. That's the involution law. So when you take the complement of a complement, it becomes the element itself. Okay? Now, the last one, which is the complementation law. The complementation law says that A union A complement will give me back universal set, and A intersecting A complement will give me back the null set. Now, how do we prove this? Very quick and fast. Let's use an example. If A is 1, 2, 3, 4, 5, and universal set is 1, 2, 3, 4, 5, 6, 7, 8. Now, A union, what will be the complement of A? A complement 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8 is the complement. 6, 7, and 8. So, for 6, 7, 8 being complement, if I now add A and A complement, what would that give me? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that means A plus A complement always gives you back universal set. Okay? Now the next one, A intersecting A prime, or A complement rather. Now, this is A already, intersecting A prime, or A complement. Now, is there anything common between 1, 2, 3, 4, 5, and 6, 7, 8? No. That is why the answer said it was an empty set. Are we good? Alright, now these are all the laws that guide the operations on sets. Now let's see what else we have here that we need to cover. Yes, the last but not the least is De Morgan's law. And with this particular law, you could still add that when you when you take the complement of an empty set, it will give you what? The universal set. Opposite of empty, full. Okay? And when you take the complement of a full set, what happens? Empty set. Because so far it's a full set, then whatever is not in it is perfectly not existing. Okay? I just have law under that. Then the last law, which is the 8th law, cleaning this now, is the De Morgan's law. De Morgan's law is kind of interesting. I wish I had enough time. And I wish the scope of the study would have allowed us to use some terms to prove De Morgan's law, or then we would only be writing this for references. So for De Morgan's law, number 8, De Morgan's law. So here it says that A union B complement is the same thing as A complement intersecting B complement. And the other one is the intersection sign. A intersection B complement is the same thing as A complement union B complement. Now this is De Morgan's law. We're part of on the scope of the study. We will not be going as far as proving this, but then should we have the opportunity to, then we will. Alright? Now this is all under the operations on sets. Now let's see what else is here and what else is not here. Okay, finite and infinite sets. So when a set, finite and infinite sets, So finite sets, they are sets with n elements. You can count them. You can say yes, this element has this set has so amount of elements. The infinite set does not have amount of elements, so you cannot actually count how many are there. Now, what do we call the next part we're talking about is what we call the countable and uncountable sets. Now, countable sets are those sets that contain what? Finite amount of elements that can be arranged in a sequence. Okay? The amount of finite elements, okay, that can be arranged in a sequence. While uncountable means the elements cannot be arranged in a sequence to give a standard number or a standard count. All right. Now we have come to the very end of set theory. I believe you have been able to learn one or two things. Should there be questions, you can hit us in the comment section. And yes, do not forget to like and subscribe to Scholars Forum. This is all for now. I remain your humble person. You know my name already. If you don't know my name, don't worry. You will say my name later. So yes, I'll catch you up later. Have a good day.